So this is what we had done in this question. We had revised Nmr, and we had revised mass spectroscopy as well. And this is what we had figured out. Okay, I'm just going to quickly go through this, try and do this question. Starting with this one, that it contains 7 carbon atoms. For that, I told you that the number of carbon atoms, the formula is it was, we already did this. It was 100 over 1.1. We did the whole probability thing, and the m plus 1 peak height divided by the m peak height, and we got 7 out of that. Okay, we did that. Suggest the molecular formula of the fragment at mass to charge ratio, which is given as 91. So the first thing is that which was given at 91, and he said 2 compounds. The mass spectrum of F has a peak due to the molecular at 106 and 107. We found out that it had 7 carbon atoms, right? And remember that it had 7 carbon atoms. 2 of the Fs were joining together to form G. And he told us that the mass spectrum of G has a peak due to the molecular ion mass charge ratio at 212 and a major peaks at 91 and 105. So these were fragments I told you. Let me just quickly revise. I told you that when you do mass spectroscopy, you not only get big peaks, but you also get these tiny fragments. And he's asking us to identify one of these fragments, the one at 91. And he says both F and G contain oxygens and are neutral compounds which are soluble in water. And the NMR spectrum of F includes a singlet peak at 10 due to 1 proton. And we figured this one out as well, that that in the data booklet. Okay, this is something that we did yesterday, that I told you that NMR spectrum, the hydrogen protons, they act as tiny magnets, which can align with the external magnetic field, or they can oppose the external magnetic field. They have 2 states, and they absorb frequencies and they gain energy from those frequencies, and they go into opposing spin. Now, the thing was that the energy that is needed to go into opposing spin or to oppose the external magnetic field depended on the chemical environment, like how much the proton is shielded by an electron. So it depends on what it is bonded to. So this is something that we did, that the resonance frequency depends on the chemical environment or the electron cover that the proton has. So we did all of that you'll have different types of hydrogen protons. Now in the data booklet, he says that there was a resonant frequency at proton 1, or sorry, 10, which I think is this one. So at 10, the only thing we figured out was it must be a carboxylic acid. You had an amide choice as well, but it must be a hydrogen proton that belongs to a carboxylic acid. So that means that the H NMR of spectrum of F includes a singlet peak at 10 due to 1 proton. So that has to be a carboxylic acid. So we know that F is a carboxylic acid. Is this clear? The hydrogen proton is resonating at 10. We figured that out from the data booklet. And the NMR spectrum of G includes a singlet peak at 5.1 due to 2 protons, which we were actually not able to figure out. And when G is heated with dilute sulfuric acid, benzoic acid, and phenyl methanol are produced. Now that's kind of gives it away that what could possibly be G? Like G must be an ester. G must be an ester because you've got he's saying because dilute sulfuric acid hydrolyzes the molecule. So it must be an ester. It must be a benzene. C6H5 is benzene. Remember that. And it's a carboxylic acid that must be bonded to this phenyl methanol, which is again a benzene with a CH2. And an OH. So because dilute sulfuric acid, remember that dilute sulfuric acid is used to hydrolyze esters. So it must be an ester. The OH would be lost and the H would be lost. So this must be the formula of G, that it must have an ester link in between. When you use dilute acid, G gets hydrolyzed. Is this clear? This last part, when G is heated with dilute sulfuric acid, benzoic acid, and you got an alcohol and you got a carboxylic acid. So it has to be an ester. Is this clear? Rupa, is this clear as well?
Yes.
Yes, sir.
So now he's saying in the question that he did mass spectroscopy of G. Right? He said that he did mass spectroscopy of G. And I told you that when you do mass spectroscopy, like if we go back to mass spectroscopy, I told you that when you do mass spectroscopy, you got a big molecule, and that big molecule breaks down into tiny fragments. So you got these molecular ion peaks, which are really heavy, which have greater mass. Remember, deflection can be, the deflection gives you an idea about the mass of the particle, which is how you calculate the mass of the particles. So you have this molecular ion and you have these tiny fragments. Now he's saying that G has a peak. This one. The mass spectrum of G has a peak due to the molecular ion at 212. So first thing is we need to figure out, is this 212 or not? Because our hunch is that this is G, because G is being hydrolyzed to form these two things. I just connected them together and formed this molecule back again. So can you even quickly calculate this? Is this 212 or is this not 212? So it's how many carbons? I think that's 7 plus 6. Both sides are 7 actually. Both sides are 7. You've got 7 carbons here and you've got 7 carbons over here. So that's a total of 14 carbons. So what's 14 carbons? 14 into 12. That's 168. Then you've got 2 oxygens. So that's 32. And that's 200. And now I need 12. So how many hydrogens I've got? I've got 5 over here, 5 over here, and 2 over here. So that is 212. So 212 is correct. This is what he's talking about. This molecular ion that he got was 212. Now he's saying that when he was doing the mass spectroscopy, he got 2 fragments as well. Some major peaks at, which means he got these particles as well, which were these tinier particles, 91 and 105. Which is basically the molecule breaking apart. When you're doing mass spectroscopy, when you ionize it, the molecule breaks up into smaller pieces as well. And you get these smaller pieces, their deflection as well in the mass spectrum. Molecular ions plus the small tiny pieces, they get deflected more because they are heavier in mass. Sorry, they're lighter in mass, so they get a bigger deflection. So the question now is, what is 91? 91 is going to be a fragment or tiny piece of this thing. So we just need to figure out what is 91. So I'm going to go with this, like, we just have to do trial and error. So let's go with this, that the molecule breaks up. When you're doing mass spectroscopy, you got this tiny fragment. So C6H5, so that's 12 into what? 6 carbons. Plus another carbon, that's 12. Plus there's an oxygen, so that's 16. And that gives me 100. So that I'm already out of range. I need 91. So maybe I go with this one. So C6H5. So I'll just rub this off. Remember, I'm looking for a fragment or a piece of this molecule that is 91. So C6H5. So 12 into 6. 72 plus 5 hydrogens. 77 plus, let's add another carbon. I mean, I'm adding the next carbon over here. That's 12. That's 89. And then I add 2 hydrogens. That is 91. So this over here, this fragment over here must be the fragment. This is 91. This is exactly 91. So the formula of the fragment is going to be C6 and H5, and it's going to be CH2. It's going to be CH2 positive. Always remember that when you're doing mass spectroscopy, ions are getting detected. So always put a positive charge on them. You're always detecting positive ion. That's it. So I'm going to put the fragment is C6H5, CH2 plus 1. The other one must be 105. I mean, probably this one. I mean, this fragment would probably be 105, because he told us that he got 2 fragments. One was at 91 and the other one was at 105. Is this clear?
Yes, sir.
Sir,
Yes.
what happens if it's not an ester? So how do you break the compound?
Over here, it is an ester. I mean, you don't have a choice. If it's not, I mean, you can break the compound anyway. Remember the fragments, like over here, when you're doing mass spectroscopy, you ionize a molecule and you deflect it through a magnetic field, right? Now, the molecule could break at any point. Like, it doesn't really matter. You could get a CH3 plus 1, you could get a CH2 plus 1. The COH might break off, OH might break off. I mean, it could break at any point. Is this clear?
Yes.
So, I mean, the only thing he said was that you were getting some major peaks at 91, which means you were detecting a particle which had a mass of 91, and another particle which had a mass of 105. So, so when the fragmentation happened, you were getting this particle. So, I mean, it could have been any particle. It could have been C6H5. It could have been a CH2 particle. A CO group can be detected, right? So the molecule could break at any point in any number of pieces. So the next one is suggest the molecular formula of F and G. We already figured that one out. So that is G. Okay, we figured that one out. The bigger question is, what's the formula of F? Now remember this, that the formula of F is, what information do we have about F? F, remember, he told us, like, if I rub off the other things, to get this one, I mean, forget G at the moment, forget the fragment thing. So we need to figure out what F is. And he's given us the only information. I mean, we figured out G, okay, that's done. So what information did we have only for F? That it had a mass, I mean, MOV is mass, TK, mass to charge ratio. So it's basically mass, because the charge is +1. So the mass is 106, and you have, due to carbon isotopes, you've got 107, right? So the MR is 106. Whatever you have an MR of 106. You also know that it has 7 carbon atoms. They already told us. And you did the MM+1 thing, and you figured out that it has 7 carbon atoms. Then they told us about the Proton Nmr, that there was a proton that was resonating at 10, and we figured out that it must be a carboxylic acid. So probably a carboxylic acid. F is a carboxylic acid. And that's it. That's the only information that we are given. And they told us that 2 of the F's combine together to form G. So this G thing is getting formed when two F combine together. That's 2 moles of compound F react together to form compound G. So it's a 7 carbon atom molecule. So I'm going to just think of this one. I'm going to make something that's 106, but that kind of makes this thing. And it's a carboxylic acid as well. So what possible, what possibly it could be? It could be, so let's go with, I mean, forget G at the moment. remember, it's going to have, I mean, the only confusing part is two F's combined together, right? To form G. Now this must be F and this must be F as well. But the thing is, I mean, they told us that they react together under suitable condition. Now these two things look different. I mean, they kind of look different. I mean, this looks different compared to this one. So the point is, I mean, F over here must have undergone some treatment and it might have changed into something else. F over here might have undergone some treatment. It might have changed into something else. So, but whatever treatment it went, there are some similarities that it must be C6H5 on both sides. I mean, that's a benzene. And there must be a C6H5 on this side as well, right? I mean, let's ignore this at the moment. And he told us that it's a carboxylic acid, right? He just told us that over here that the H-Nmr spectrum of F includes a singlet peak at 10. So it must be a carboxylic acid. And it's got 7 carbon atoms. So the only choice I've left is, I mean, that's the 7th carbon atom. So I'm going to make it a carboxylic acid. I'm going to just see, I'm going to just check, can that be F or not? Is this 106 or is it not 106? So we can just have a look quickly. Is this 106 or not? Because remember, it's a 7 carbon atom. I'm assuming 2 Fs are combined together. So it has to be, I mean, it's got to be a benzene over there because there's a benzene on the other side as well. So both sides must have benzenes. The 7th carbon atom must be the carboxylic acid. So let me just check whether that's 106. So 7 into 12, that's what? 7 times 12 is 84 plus 2 oxygens. So that is, can't be 2 oxygens. That's because as soon as I add 2 oxygens, as soon as I add 2 oxygens over here, 7 carbon atoms and 2 oxygens, and the mass spectrum of F has a peak at 106. So as soon as I add 2 oxygens, I don't get, I actually cross 106. So what about this side? Maybe it's an alcohol.
So it can't be alcohol because it's insoluble in water.
Yeah, I'll talk about that later. Okay, just a second. Let's say if we can make 106 or not. So again, 12 into 7, that gives you 84. Plus there's 1 oxygen, so that's 16, that's 100. Okay, that's good. And then there are how many hydrogens? That's it's got 8 hydrogens. It's got C6H5, and it's got how many hydrogens? It's got 5 over here, 2, 7. So that even crosses 108. So this one crosses 108. I mean, we need 2 hydrogens. We need 2 hydrogens lesser. So what do we do over here? I mean, you need 2 hydrogens should be lesser, right? So how do I, because I'm crossing 208 and the peak was at 106. So how do I get rid of 2 hydrogens? I'm just going to, so it can't be an OH. I mean, you're right. It can't be an OH because he said that it's insoluble in water. So what I can do is, remember, alcohols, carboxylic acids are linked with aldehydes, like you can interchange them. So I'm going to go with, because I need to remove 2 hydrogens, right? I'm very close to 106 now. So what I can do is I can turn this into double bond ONH. Now this is exactly what? This is exactly 106. Okay, now this is exactly 106. So it's an aldehyde. F is actually an aldehyde. So that required a lot of trial and error. And remember, all these questions are like jigsaw puzzles which you have to solve. So this comes out to be around 10. It comes out to be exactly 106. So what's going on now? Now it makes a lot more sense. What's going on over here is that an aldehyde can be turned into a carboxylic acid, and an aldehyde can be reduced to turn it into an alcohol. So this is what's going on. So how do two Fs react together to form this thing? Because one of the F atoms, okay, let's ignore this now. So one of the F atoms is converted into a carboxylic acid. So it turns into C6H5 and C double bond O and OH. And the other F, an aldehyde, could be reduced back into an alcohol. So the other F gets reduced to an alcohol, a primary alcohol. And now the two things react together to form an ester. So that's how compound G was actually getting formed. So the question is, where did I wrote carboxylic acid, so this must be wrong over here, because they said that there was a proton that was resonating at 10. So I'll have to, I think, double check this. Is there a proton resonating at 10? Can we find aldehyde somewhere? Yes, exactly. I missed out on the aldehyde. The aldehyde, I didn't see this. Aldehydes, the hydrogen protons of an aldehyde also resonate around 10. So that was probably a mistake. I didn't actually, I just saw this carboxylic acid at 10. So I just wrote that down. Aldehyde was also an option. So I think we have pretty much solved the whole puzzle now, because we figured out that this is an aldehyde, that's F. And how do two Fs react together to form compound G? It's because one of them turns into a carboxylic acid and the other F turns into a primary alcohol. Okay, is this point clear?
Yes.
Okay, Bakiyon clear, Ruba, is this clear? Nabila, Minahil, is this Zoha? Zoha, did you get this?
Yes.
Yeah.
Yes, sir.
Okay. So so we've figured that out. Okay. So remember, all these questions about NMR and especially the ones, you always get this one question. It's like solving a puzzle. So and it's time consuming. So you have to be very quick with this. So suggest the structures of compound F and G. We've figured that out. So on the structure you've drawn, circle the protons responsible for the H NMR peaks at 10 in F and 5.1 in G. So we figured out the 10 in F. We figured out the 10 in F, that was this one, the aldehyde peak, this one over here. You get the one in green over here. What about G? He said that there was some peak at 5.1. So who's giving a peak at 5.1? Remember, hydrogens are the ones that resonate. So you've got, so we just have to look for that. You've got hydrogens. So let's look at the environment, chemical environment. You got benzene hydrogens, right? Attached to aromatic ring, so they're out of the question. They're probably not going to resonate at 5.1. So they're gone. The ones over here, they're gone. C6H5, C6H5. These hydrogens are gone. What about these hydrogens over here? Would they resonate at 5.1 or not? And remember, he basically the hint was, he said that the spectrum of G includes a peak at 5.1 due to 2 protons. So it's got to be these two. These two protons are exactly in the same environment. They're exactly in the same environment. If you do the Proton Nmr, there would be 3 peaks. These hydrogens are slightly different. They're very similar to each other. So they're going to resonate at 1 frequency. These two hydrogens are different. They have a different chemical environment. They're going to resonate at frequency number 2. And this benzene hydrogens are different from this benzene hydrogens, because this benzene is bonded to C double bond O. So the electron cloud would be slightly different, differently distributed. And the shielding over here for the hydrogen proton would be different. This C6H5 over here is going to be, different compared to this one, because it's bonded to a CH2. So the electron cloud over here, remember we did the electron donating and withdrawing effect. So it's going to be different over here. So this is going to be, let's call that F3. As anyways, he was very specific that there were 2 protons. So it must be these 2 protons. So we don't even have to look at the data booklet. Those are the only 2 protons that are in the same environment. So we can circle that. Now describe and explain the relative acidities of benzoic acid, phenylmethanol, and 4-methylphenol, this one. So it all depends on the negative charge over here. So let's assume that all of the H+1 ions are lost. Remember, we did the whole electron donating withdrawing thing. So let's assume that all the H+1 ions are lost, and when the H+1 leaves, the remaining ion becomes negatively charged. So negative charge over here, and you got an H+1 over here. So the thing is that this one is going to be the strongest. I mean, the first one. Why is it going to be strongest? Because I mean, let me even rub off the two oxygens and draw the whole structure. So you got an oxygen which has a -1 charge over here. So the first one is going to be the strongest acid. Strongest acid is the one that doesn't attract the H+1 back. It wants it to leave. It dissociates. So why would it dissociate? Because there's a lot of electron withdrawing effect, because there's a negative charge over here. There's an oxygen that's pulling the negative charge, and the negative charge might also overlap with benzene's electron cloud. Remember, benzene has an electron withdrawing effect. Electrons over here will overlap with benzene's electron cloud, and they're going to get distributed. So the negative charge is going to be lesser, which means when the H+1 is leaving, it's not going to attract it back. It's not going to pull it back. It will allow the H+1 to leave, because the negative charge is going to be lesser, because the negative charge gets withdrawn towards the other oxygen, and it also gets slightly withdrawn to the benzene, or mixes with the benzene pi electron cloud. Is this clear? This thing?
Yes.
So you're going to talk about, I mean, you're going to, what you're going to write, or the way you're going to explain this, that oxygen in C double bond O, you can talk about C double bond O in benzoic acid, has an electron withdrawing effect. Which decreases charge density. So it decreases charge density on the COO -1 ion, making it stable, which basically means it's not going to attract H+1, because the negative charge is going to be a lot. It's going to be very less, because it gets withdrawn or pulled towards other things. So RCON making it more stable, actually. Hence more dissociation. So hence there's going to be a lot more dissociation. That's the first one. So now we are left with with 1 and 2. So over here, which one is, remember I told you that phenols are kind of more acidic compared to alcohols. Why? Because now this one is a normal alcohol. Remember, this is not a phenol. For it to be a phenol, the OH must have been directly bonded to the benzene. Over here, it's not directly bonded to benzene. Now what happens over here is, this is a phenol. This one is the middle one. You got an oxygen atom, and the oxygen atom will have electrons, because when the H leaves, it leaves its electrons. So there's negative charge over here. The negative charge mixes with benzene. So, I mean, compared to this one has more electron withdrawing effect, because not only does the negative charge mix with benzene, but it also has an oxygen, and that oxygen also withdraws the electron. But over here, you just have the benzene. That's it. So which is why this is the middle one. Okay, usually you don't. So this is the one which would be medium acidic. Okay, this is the middle one. You usually don't comment on the middle one, but the negative charge would overlap, and the negative charge density would decrease, but it won't be as less as this one. So the H+1 will dissociate, but the negative charge would still be relatively higher compared to this one. This one is going to be the most acidic, because there's not going to be any withdrawing effect. Why? Because the oxygen is not bonded to a benzene. It's bonded to a carbon chain. And what do carbon chains do? They actually have an electron donating effect. So, which is why the negative charge, or at least it's not bonded to benzene. So there's no electron withdrawing effect because benzene is kind of far away. The lone pairs can't really jump from this end and start overlapping with benzene's electron cloud over here because there's a CH2 in the middle. So the point is that over here, there's not going to be any withdrawing effect. So the negative charge over here is going to be large. And if it is large, so what it will do is that it will attract or pull the H+1 back. It's not going to let it dissociate. So you're going to talk about phenyl methanol and you're going to say that it's an alcohol. I mean, this one. So we can write about this one. So you can talk about this, that this is an alcohol. And you can say that alkyl chain has electron donating effect. Which increases the negative charge on what? On this O-1 ion, making it unstable. So making it unstable, and it will, which is why it's going to be a weak acid, because it will immediately attract, because the negative charge is large, so it will immediately attract the H+1 back again.
Sir, in methylphenol, it
Hanji.
has an alkyl chain as well, but we are not considering it as a weak acid because it has a phenol in it.
Nee, this one, this chain, right?
Yeah, this one.
Nee,
Yes.
the problem is the OH is not, has nothing to do with the methyl. It's bonded to a benzene, right?
Right.
So, I mean, for example, over here, I just ignored the benzene because the OH group was not bonded to the benzene. It was actually bonded to the carbon chain. Okay.
So whenever the OH is bonded directly to the benzene ring, that's more acidic.
That's more
Like the
acidic.
phenol.
That's more acidic because the lone pairs, I mean, the negative charge over here will mix with the benzene electron cloud. Clear?
Thank you.
Just 1 second. वो किधर है? So next one, you've got an ester over here, and he says suggest a two-step route for the synthesis. So there's the previous one clear, everyone? All clear?
Yes.
Okay. So and remember, it's always a comparison. It's always going to be a comparison when they talk about acids. A lot of time, it's just a comparison of carboxylic acid with a normal alcohol. Remember, this is a normal alcohol, a carbon chain with an OH, and this is a phenol, a benzene with an OH. So it's always a comparison between these three. Sometimes there's going to be a comparison between benzoic acids. Like, I mean, they might do a comparison, like they might give you another benzoic acid. And exactly same thing. Okay, so sometimes they might do a comparison between benzoic acids. So there are two benzoic acids, and this benzoic acid has an NO2 over here. That's the only difference. Okay, so you might get a question. Usually you get a question between a benzoic acid, I mean a carboxylic acid, an alcohol, and a phenol. So what if you have two carboxylic acids? So now they're kind of similar. So the differentiation is gone now, because that also has an electron withdrawing effect. Okay, right? Because it also has an oxygen, so the electrons are going to get withdrawn. It's got a benzene, the electrons are going to be withdrawn. So that factor is kind of the same. So what's the only difference now? The only difference now is the NO2 group. Remember when we talked about electron donating and withdrawing groups? It's given in this one is an electron withdrawing group. So the point is that the negative charge over here is going to be more withdrawn because you got a double bond O, so that's the same. You got a benzene, so that's also the same. The electrons get withdrawn towards the benzene. But over here, the electrons are going to be more withdrawn because there's an NO2 that is pulling electrons from the other side. So the electrons over here on this side are going to be more pulled towards the other side. So that's going to be even lesser. So if I do a comparison between these two benzoic acids, then this one would be the stronger acid because it's going to have a lesser negative charge. Okay, I mean, these factors were kind of the same, but because of the presence of an NO2 group, which is an electron withdrawing group, the negative charge gets pulled even further towards some other thing. Okay, so the negative charge is not going to be here. So it's not going to attract the H+1 that strongly. Okay, is this clear?
Yes, sir.
So the next one is suggest a two-step route for the synthesis of 4-methylphenyl benzoate. I mean, this one. From 4-methylphenol benzoic acid. So first thing is you have to synthesize this and include reagents and condition and structure for the intermediate compound. So it's probably an ester. I mean, it is an ester actually. And he's saying suggest a two-step route for the synthesis of 4-methylphenyl benzoate from 4-methylphenol and benzoate. So that's easy. I mean, you just have to sort of join them together. That's it. You've got this one, OH, and you got a carboxylic acid. That's it. So you just have to kind of connect them together. So here's what's happening. You've got a benzoic acid. And you've got methylphenol. So phenol OH would be over here. And you got a CH3. You just have to connect them together in the middle. Now there's a catch over here, and that is that which we probably haven't done in organic, but I'm just going to quickly, where's the, so this is the thing that we're doing. So I'm just going to do this over here, which is that when you form esters, there's a problem when you're trying to form esters with phenols. And that problem is that why does esterification happen in the first place? You can remember you've been studying esters since O levels. The OH would be lost and the H would be lost. But the question is, why would that happen? The reason that happens is that you got a carbon atom that's very strongly positive because it's bonded to an oxygen, and you've got lone pairs on this oxygen on the other side. So what happens is that it starts attracting the lone pairs, and the positive carbon over here starts pulling on those lone pairs. And the H and OH, they kind of get repelled. When the O and the carbon get together, the H and OH, they get knocked out because the oxygen is coming in. So the OH and H, they get repelled, and eventually water is formed. But the problem with phenols is, where's the lone pair? I just told you what happens to the lone pair when you have a phenol. The problem is the lone pair is not there. The problem is that the lone pair is actually mixing with the benzene electron cloud, which means it's got a low charge density. Because a lot of the electron cloud is actually overlapping with, it's overlapping with benzene's electron cloud. So it's going to have a low charge density. Is this point clear?
Yes.
So the thing is that the positive charge is not really strong enough to actually pull these electrons or get attracted to these electrons, because the electrons are not even there in the first place. The electrons are overlapping with benzene's electron cloud. So the thing is that the positive charge has to be stronger. It has to be, you have to somehow make it stronger. You have to make it stronger so that the lone pairs don't mix with benzene and they kind of get attracted to the positive charge over here. Is this point clear, Ethan? Mohammed, is this clear? Yumna, is this clear?
Yes.
Okay. So, so you have to kind of pull the lone pair. So the positive charge has to be stronger. So what you do is, instead of a carboxylic acid, you actually use an acyl chloride. You use an acyl chloride, it's going to have Cl. So in acyl chlorides, you got two electron withdrawing elements attached, two electronegative elements attached. So the positive charge becomes stronger. And now the lone pairs will get, instead of overlapping with benzene's electron cloud, the lone pairs will get attracted to the really strong positive charge over here. So remember this, that you can't make an ester with the phenol. Phenol is not a normal alcohol because in phenol, the lone pair is mixing with benzene's electron cloud. In a normal alcohol, the lone pairs are still there. So you have to pull those lone pairs back. So you need the positive carbon over here to be a lot stronger positive carbon atom. So a carboxylic acid wouldn't work. It has to be an acyl chloride. So how do you get rid of the OH and turn it? You add PCl5 plus heat. I mean, that's the first thing. So the first thing is you take benzoic acid and you add, react it, you add PCl5 plus heat, and benzoic acid turns into an acyl chloride. And then you can do esterification. And that's how esters are formed. Is this clear? Which is why it's going to be a two-step reaction, because the first thing is esters can't be formed using carboxylic acid with phenols. It's got to be an acyl chloride. So that's the first step, PCl5. And then you can form the ester. And for that, you usually use alkaline conditions. NaOH aqueous is used, for this part. Why do you use NaOH aqueous? That's another story. That's because you want to get rid of this H over here. And phenols, remember, are acidic. So phenols will lose the H. We just studied this, that phenols were kind of acidic. So phenols are going to lose their H to NaOH. So that is kind of going to make the process easier. So alkaline conditions are used, and that's how esterification happens. So here, let's continue tomorrow now, okay? Okay.
Sir,
Yes.
if we have some other questions, वो हम इसी class में कर सकते हैं बाद में?
हाँ, ठीक है.
Thank you, sir.
Okay. Allah Hafiz.
Thank you.
Sir, just one question.
Yes.
Our organic chemistry is completed or what?
No, we can try and do organic on Friday. I think it's more, let's say it's 70 to 80% complete. We did.
Okay, sir.
Okay. We did the last part, the nitrogen compounds we haven't done, so we'll do that. Okay.
So which chapter is this, like HNMR and all?
Those are the chapters that are right at the end. Analytical, like
Practical, I think. Yeah.
Analytical chemistry is right at the end. Okay, so we'll cover that later in a lot more detail. Okay.
Okay,
Okay,
sir.
sir.
Okay.
Okay, take care. Hafiz.